Like, what do you?
He's so rude. Sorry. Good.
No, it's okay. I'm just
Yeah, you're
wondering
right.
the steps. So the
Yeah,
first thing you do is divide by 2, but then you have sine 2 theta. Do you divide by 2 again?
nope, not yet.
See, that's where I'm
So
lost.
let's do this one.
Okay.
All right, here we go. Buckle up, everybody. So the first step would be to divide by 2.
Hmm.
This says sine of some angle is a half. So what angle would make that happen? And I don't know. This problem was, screw it. We're just going to find all the answers. Give me
See,
the most basic angle that makes sine 1/2.
um, oh my God, noises.
Sorry, I need
Um,
to turn.
no, it's okay.
What you got?
Pi over 6.
Let me come back here. Wait a minute. Where am I?
Okay.
All right, let's see. Yeah, pi over 6. Sine doesn't like it close to the x-axis. Where else?
Then it would be 5 pi over 6 also?
Good. It'd be up here in the northern hemisphere. I like it. Is everybody out there with us?
Yes.
Yes. Okay. And then it would be plus 2 pi k. Is that cool? And of course, the book put plus or minus. So well, we're fine with that.
Okay.
So we're not done yet.
Yeah.
But the first step is say, oh, 3 theta. That's one symbol. That's the 3 theta 0 symbol, right? It's hard to say that fast. I hope you understand what I'm saying. So it's not the first few steps are not any different as if this was just theta.
Right.
You figure out what 3 theta is, and then now you divide by 3.
Oh, okay.
So then you get theta is pi over 18, give or take 2 pi over 3k, or theta is 5 pi over 18, give or take 2 pi over 3k. I always do this, even if they want answers on 0 to 2 pi, especially when it's got some freaky shit inside, because now I can just pick values for k and build up all my angles until I reach the upper limit. Okay. You guys, so this is what I showed you. And again, it's been a little while, but
yeah.
All right, is everybody else okay out there? Because I am starting to get some 9.5s trickling in.
Because you know what we all did, right?
I told you what you did last time.
We do this every time.
Yes. And it's understandable. So, I mean, I try to be honest with you guys about, and this is true for most teachers, no matter what they say. Some of them more hard asses, but they assign homework, they assign due dates, but this is your class. This is your education. You do what you can when you can, so you are ready for the quizzes and you're ready for the final. And if I start, writing real big, finish this or redo, correct, blah, blah, and you're like, all right, I'll do that when I can. I mean, that's right. And I'm not going to say that I'm going to be not taking points off or not doing homework, but homework is worth much less than all the quizzes and the final. So, I mean, it's supposed to help you get ready. So that's enough of that. I've said that several times. Any other questions? Anybody else or more questions? From Amber, anything?
Yeah, I have more if nobody else has anything.
You can be their hero. Go ahead.
Okay. Well, hopefully. Number 27.
All right. So, I mean, so first thing to realize is there are, let me get my little, the big problem is the fact that there's sine, oh shit, I put that over there. There's sine and cosine running around, right? You've got this, which seems kind of tempting to do something with it, but then your angles aren't going to match, right? I don't know if you guys get what I'm saying.
Mm-hmm.
So that is sine of
2x.
but then your angles won't match. So that doesn't
Right.
seem like a great way to go. So what else could we do here?
I got nothing.
The funny thing is, you guys ready? Here we go. You guys ready? I don't know if you guys are ready. Oh, I got a chat coming in. Let's see what it is. Oh man, it's for the next section. Oh, all right. We'll get to that, Nathaniel. Don't let me forget. Oh, somebody else chatted before that. I'm sorry. I keep missing these. Yes. So watch this. How many terms are there?
Terms like four?
Yes.
Like 2
4.
sine and 2 cosine? Okay.
What do you do with something that's got 4 terms when you are thinking about factoring? Because it's equal to 0. It'd be great if I could factor this thing, right?
Mm-hmm.
In the chat, somebody told me, and I think you meant this much because there's no signs over here. Can't you take a sign out of the first 2?
Ooh, yeah.
I'm grouping. I'm using grouping.
Mm-hmm.
If you do you notice how you'll have 2 cosine minus 1?
Yep.
Just like this says?
Yep.
So then you can do the last step of grouping. You got the 2 factors, blah, blah, blah. Okay. But I understand when you first look at a thing, it's like, what the shit? Right?
Yep.
Number 25 is very obvious that it's factoring. Number 27 is not obvious that it's factoring, but that's what you try. When no identities work in these equations, think about factoring, because that's something I use for a lot of equations, especially when it's equal to 0 already. That's kind of they're trying to give you a hint. I'm not saying it's obvious, right? Just saying it's easy for us to forget that we can do that.
Yeah, I think I just looked at the 2 sine of x and went down that road, and then I got stuck.
Oh, yeah.
Okay, thank you. I'll let somebody
Sure.
else go.
All right. How's everybody else? Anybody else? Oh, I did have a question from the next section. Are there any more questions from this section before I go to the next section? No. Man, you guys are freaking me out a little bit. You guys out there? All right. So let's see. I got a question from 10.1. Can you make it a little more? So the question from 10.1 is sort of a general one. How do I know if I'm going to have, the way you put it is a little interesting, 1, 2, or 3. There can only be 0, 1, or 2. There is a possibility that they give me a triangle that's impossible. So I could have 0 triangles. I can have 1 triangle. Oh yeah. And this is another situation where it's been a little while since we did these. Let me see. What question? I think 21. Okay. Yeah. So let's do 21. Why not? This will be a twofer here. This will be a nice review, and it's a homework question. So why not? Oh, I got another chat. I can't handle all this technology. Hold on. Or 24. Whatever. All right. We'll do one of these. Let's do 21. What is the instructions here? Oh, I see. So this question is no triangle, 1 triangle, or 2 triangles. So let's see. Let's try 21. So if I draw this for myself real quick, and it doesn't really have to be to scale, but I normally try to make, well, I kind of failed here, but I normally try to make a smaller side, a middling side, and a longer side, but it doesn't really matter. So I'm going to make this 5. So this is C. I'm going to make this 13. And then I'm going to make this A. So that makes this angle A. This makes this angle B, makes this angle C. Is everybody with me so far? That is just my anchor triangle. Is that how that triangle looks? I have no freaking idea, right? I do not know. I do know, oh, and again, which side does this go with? What can I replace this with one of our letters?
C.
Good. So if you really want to, you can make alpha A, you can make beta B, which is basically what it is already, and make this gamma dude C. If you want to, you don't have to, right? But it's kind of nice when you have lowercase a goes with the uppercase a and all that kind of shit. Do you guys remember the idea? Oh, let me put that one piece of information. So now we know C is 10 degrees. So what is it about this triangle that tells me law of sines will work? Do you guys remember?
You have one complete set.
I love it. I have a complete ratio I can make. So the idea of law of sines is, holy shit. All right. Is that right? Or you can vice versa them, right? Doesn't really matter. So I can make a complete set with the C's, right? So I can make sine of 10 to 5. And now I can set that equal to, what's the only other one I can really work with at the moment?
Angle B.
B, that's because A, I don't know shit about. So I need a complete set, and then I need something just missing one thing. So here I can put sine of B over 13. Can somebody remind me what is the fundamental reason that there might be more than one triangle that answers these parameters, that answers these conditions? What trigonometrically? Well, let's see. What am I going to have to do to solve for B here? That's right, kids. I multiply by 13. Bueller. Is everybody cool with that? And then what do I do? How do I solve for angle B?
Multiply by the reciprocal.
Be really careful. No, I think you know what you mean. I'm going to take the inverse sine of both sides. And I really hope you're not taking this as being picky or something. It sort of is, but I don't know if this is what you meant. I think this is what you meant. All right, maybe. So
I would have taken the reciprocal both sides and then I do the inverse. I don't know if that works too.
The only reason you'd have to do it, if you have to reciprocate, is if the thing you're trying to solve for is on the bottom.
Okay, maybe that's what I was thinking.
Yeah, sometimes the thing you're trying to solve for is on the bottom, so you have to reciprocate. In this case, sine B is on the top, so I can attack it directly with this guy.
Okay.
Well,
These
wouldn't you just
cancel. Go ahead.
multiply-
Sorry.
Wouldn't
Oh,
you
sorry?
just multiply like the 5 in the sine B and then the 13 in the sine 10 and then do the inverse afterwards?
Yeah. Well, all right. All right. So here's what it started off as. Now watch, guys. So what you're saying is basically, couldn't I have cross multiplied, right? Is that what you're saying?
Yeah.
Yeah. Cross multiply. I really want you guys to accept cross multiplying and then realize that it is not very often the best thing to do. Because look, now I got the 5 over there and it really didn't need to be there. I need to get rid of it again. So I pushed it up and then I pushed it back down. It's like, okay, what the hell? The only thing that was in the wrong place in the first place was 13. That's why all I did was bring him up. I'm going to leave the 5 right where it is. Do you see that? So there's nothing wrong with this. Please understand. There's nothing wrong with cross multiplying. It's just more work. It's like, move that barrel over there. Now move it back. Now do that all day. It's like, holy shit. We're not in the military. I'm not going to make you do that. You guys with me out there? Okay. So again, your suggestion is not wrong. It's just extra work that you don't really need to do. So now, can somebody tell me, let me rewrite what I've got here. Why would this step be the step that leads to the possibility of two triangles. Somebody go ahead and do that for me. And this problem is in degrees, so make sure your calculator is in degree mode when you're about to do this. If you're not sure how to do that and you're too afraid to ask because you feel like you should know already, just ask, just private chat me or something. Hopefully everybody knows how to change the mode. Please let me know if you're not sure how to put this in your calculator, if you're not sure how to do anything. Oh, let's see. It doesn't. Ah, yeah. So I got somebody sent me a private message with the correct answer. So what I get when I put this in my calculator, let's go ahead and go to a couple places. 26.8. Holy macro. What? Hold on, sorry. My pen is just, okay, it's a digital pen and somehow it still has ink squirting out. I have no idea. Okay. You guys, anybody else get that same thing? Uh-oh. All right, so let's take a look here.
I'm getting a oh, there it is. Never mind. I was getting a domain error for the longest time and I couldn't figure it out.
Ah, all right. I like it. So if you did get no solution to this, that would tell you there's no triangle. If you can't even get one angle to work, no triangle. What do I have to check right now to see if there's a possibility that there's more than one answer?
It could be a reference angle.
Yes. So right now, one possibility is C is 10, B1 is 26.84, and therefore what would A1 be? If I, with this first triangle, and using exactly this degree, Jeff, this angle. What's the third angle going to be?
143.16.
Yeah, so all you have to do is do 180 minus those things. That sounds about right. Yeah, buddy. So that's one. That's why I put a little one down there. I can even put it on the C, even though he's going to be the same. Or we put it over here. So that's the first case. Please understand, I still have to figure out what. Let me put all this stuff down. Then B1 is 13. C1 is 5. And I still have to figure out what A is, right? Little a. Is everybody with me? I don't know if you guys can see over there on that side. So when you have the law of sines, you might have a set of ones and then a set of twos. I'm going to put the twos over here. I'm really sorry. So here's the second case over here. You guys see it? Second case. Let me rewrite everything I already know for sure. C1 is 10 degrees. B1 was given to me and I'm sorry, 2, Jeff, on the second case, buddy. Keep it together, my young friend. Am I young? No, that's the problem. And then A2, we don't know yet. All right, let me stop for a minute. C was given to me. B was given to me. And little c was given to me, right? So those I know. So that's the same for both cases. The difference here is going to be what would B2 be? And just like somebody out there told me, I'm sorry, I didn't catch who was talking to me. That's a possible reference angle. So what would the angle be that it might be referencing then? How do I figure out the other possible angle?
Is it 180 minus that?
Yep.
153.16.
Totally. And if that angle was 153.16, is there room for there to be an A2?
Yeah.
What do these make so far? Yeah, because these only make 163. So A2 then would be, I think this.
Yeah, 16.84.
All right, let me stop. If you do not know what is going on, you must ask me now. And that sounded like an ultimatum, but you can always ask me later too. But right now is a really good time. This is the weirdest part about either sines or cosines, the law of sines and the law of cosines. This is the weirdest part. The rest of it is just plugging stuff in the right formula and knowing how to put it in your calculator. This is the part that requires you to realize what you need to do to see. Is there another triangle? So if these two would have added up to be more than or equal to 180, that would have been no room for another angle. So there would have been no second case. But if there is leftover room, oh shit, there's a second case. So now I got to figure out, let me use my mouse because then you can't track it when I'm using my pen. See, well, I got to figure out little a1, and I got to figure out little a2. And they're both going to have.
little a 1 and
Sorry?
2 be the same? Would little a 1 and 2 be the same? Because
No.
can't you just do Pythagorean theorem?
Why can't I do Pythagorean theorem?
Oh, they're not right triangles. Never mind.
Not right triangles. You might have a problem where you do happen to get a 90-degree angle, and the minute you get that in any problem, then you can just revert to doing right triangle stuff, which is awesome. Remember, the whole purpose behind these first two things in chapter 10 is, what if it ain't no right triangle I'm talking about? And please ignore my poor grammar. Now over here, how would I get little a1? And normally I wouldn't even start on the second case until I finish the first case, and I really should have done that, but I'm sorry. How do I do little a1? Well, I can do, I can use the one I've known forever, sine of 10. I can use C again, sine of 10 degrees over 5 equals sine of A over little a. And now you can cross multiply, whatever you want to do, right? You can solve for little a. Are you guys with me? And then you would do the exact same thing. You would do the exact same thing over here. Except over here, it would say sine of 10 degrees over 5 equals sine of 16.84. That's what that is now. Over A2. I forgot my little A1 over there. All right, so now cross multiply. Thankfully, there's no inverse sine to take, right? Because you're not solving for an angle. You guys, anybody not with me on that? So in this kind of problem, when you're using law of sines, the minute you get the very first angle that you solve for, you need to consider its reference angle possibility, right? So if this angle, if the angle they gave me wasn't 10, if the angle they gave me was 50, there would have been no second triangle because there would have been no room for a second triangle. If this was 153 and the other angle is 50, that can't even be a triangle already. But it's the fact that that was only 10. Shit, that left room for this third angle to exist. Damn it. And that's why there's a second triangle. No idea what's happening out there. You guys okay? Or are you just accepting your fate? What's happening? You know, like, this is my life.
I think I got it. I have the reference angle idea part.
Yeah.
My question is, for A2, where did the 16.84 come from?
Well, once we figure out the other possibility for B,
Mm-hmm.
this, right? So this
Yes.
is what we got over here for the first triangle. Then all three have to make 180. So I just figure out that plus that and see what's left over.
Hang on. I'm processing.
Yeah. I mean, how did we figure this out?
Got it. Okay.
We do it the same way. Yeah.
Okay. I gotcha. Okay. Thank you.
You're welcome. And that's another reason, even beyond it being a right triangle, the reason the little a's can't be the same is because this a's got a big ass mouth, right? So it can fit a much bigger stick in it. And this has got a little tiny mouth. So this A2 is going to be much smaller than this A1 for damn sure. And I'm really sorry it's kind of messy. I'm hoping you followed what I was doing. All right. Anything else, guys? Did I miss anything in the chat? No. Okay. Is that good? Person who asked me, is that all right? All right. I'll take that as a yes. Okay. Okay. Anything else, guys? So just to kind of review a little bit, first two sections of 10, law sines, law cosines. Law cosines kick so much ass. Pythagorean theorem lives in it, and it just has one little extra term that's a little what do you call it? I don't know, adjustment term, right? If the angle is 90, the adjustment term goes away and you get your normal Pythagorean theorem back. It's crazy. Then we got the polar coordinates. And last time we did a graph of a kind of a freaky example. Remember that with the r squared? So we did that on Tuesday. And then we did get into polar form of complex numbers, right? So I need to finish that out tonight. And then I want to get a little bit, sorry, go ahead.
I have a question. For the quiz,
Yes.
what does it stop at? 10.3 or 10.4 for the next quiz?
Oh, that's a good question. Because I still need to, oh man. All right, so I need to update the, what do you call it? The homework sheet, right? I need to go back to that video when I was writing on the homework sheet because I wasn't actually writing on it. I was just, so I need to remember what I did with these. Where am I here? Come on. There we go. Does anybody remember off the top of their head? I still need to go back and look at the video. But I did change the date. It was supposed to be today, our next quiz, but we just had our quiz on, we just had this quiz. Yeah,
I think you changed it to the 17th of November.
probably. It sounds about right. So I have to take a look, and then I need to update this over the weekend so you guys know what's going on. So yeah, the other thing is, what's it going to cover? So the last quiz covered, the last quiz did cover 9.1 through 9.4. So this quiz will definitely start at 9.5. Yeah, and actually I think, yeah, there's no reason why it can't do 9.5 through 10.3. Notice how I don't put the graphs on there. So this is going to be, I kind of like that idea. You guys should be able to get through 10.3 done by next Tuesday, or at least enough of it looked at so you can get ready for a quiz. And I'm not even going to make you do the graphing of these polar coordinates yet. Do you understand? It's just going to be working with, what do you call it? Converting between rectangular and polar, right? Okay. So I'm not going to give you a cardioid to graph on this next quiz coming. So it will be, if it is Tuesday, I said it was, then it will be Tuesday, and it will be 9.5 through 10.3, just like it says on the homework sheet. The only thing that's changing is the date. Is that understood? Okay, maybe. All right. Okay. So anything else, guys? All right. So what we did last time, let me see, do I want to go back on the board? I think maybe so. That might be better for me. Let me stop sharing. All right. I should get a second whiteboard. That would be awesome. I know, hold on. Pull that over there. Oh yeah, I gotta highlight me. It's all about me. There we go. Okay. All right, so what we did last time is we realized, so one thing is I gave you the variable we use for complex numbers. So we use Z for complex numbers, and they're the same old complex numbers. But now we realize we can rewrite these into polar form, because fundamentally, complex numbers are like the XY plane. They're the real plane and the imaginary plane. I mean, plane. Real axis and the imaginary axis make the complex plane. Put this as a word, because otherwise it's going to get real freaky in a second. So in polar form, this will be, okay, Z equals R cosine theta plus I sine theta. I like it. How did we get R? R was the absolute value of Z, which is the same as the absolute value of anything. How far away from zero is it from the origin? So that we figured out it would just be wherever my point is, it's just going to be the good old distance formula, right? So if I got A and B, it'll be square root of A squared plus B squared. And what would theta be? Theta will be the inverse tangent of B over A. I like it. You can have all this written in terms of, if they put X here and Y there, it could be X and Y, Y over X, right? You guys, the variables don't really matter. Yes. Somebody's asking me if I'm going to make a practice quiz. Can you just do like normal? Hopefully you guys, you do this for me and it really helps you out. Just somebody email me and say, hey, don't forget about that practice quiz. Thank you, absent-minded old man. Okay, don't say that last part. Is everybody with me so far? This is very quick. And again, why does this make sense? What's R times cosine theta? What do we know R cosine theta is from polar coordinates? Even from just trigonometry, what's R times cosine theta? Tell me this, guys. Okay. Here's Y, here's X, here's R. What's cosine theta? What's cosine theta?
X over R.
All right, so what's R times cosine theta?
X.
X, thank you. Okay. R times cosine theta is the X piece, the real piece. R times sine theta is the Y piece, the imaginary piece, right? So on one level, this is kind of silly, to be honest. On one level, hopefully somebody out there is like, this is kind of dumb. So if you do write this as X plus YI, instead of using A and B, I use X and Y. Why would that make sense for arbitrary letters? Because the real is the x-axis. That's sort of like what the x, and the y is, it looks like it's the y-axis, the imaginary part, right? So x is r cosine theta, and yi is y, yi. They're the same. They're equal to each other. They're the same thing. So then you might ask yourself, what the shit's the purpose then? All we did was write the same damn thing with more symbols, Jeff. What's your problem? So it's kind of funny. I'm trying to talk this down. Man, I really hope you guys are, because the true power of this is what we started to look at last time. Very often, if there's more than one way to represent an idea in mathematics, depending on the problem we're doing, one of those 2 or 3 or 4 ways will make that problem easier. So if I have to solve an equation, maybe I can do it graphically and it's easier, right? Instead of doing it algebraically. You never know. Okay, so stay with me. Let's do one concrete example just to get us back in the groove here. One concrete example. So what if I have the number, what is it, Jeff? Oh, let's say negative square root of 2 plus square root of 2i. Let's say that's my complex number. Can somebody help me with what quadrant that would be in the complex plane?
Quadrant 2.
Yeah, because it's negative and then positive, so it'd be quadrant 2. I love it. It's going to come in handy in a minute. So can you figure out R, which is the absolute value of Z, which is just the, what do you call it, distance formula. So let's see, both of these will come out to be 2. Is that cool? I get 2 plus 2 is 4, square root of 4 is 2. Okay, that's nice. And then what's theta going to be? It will be the inverse tangent of y over x, which just comes out to be -1. That will not be the right answer. And we know why, because we've done this work for ourselves. We know what quadrant we're supposed to be in. So help me out. This is one you don't need your calculator for. What angle is this? And you can kind of, since you don't need your calculator, you can just make it show up in this quadrant in the first place.
Pi over 4.
Yes, so which pi over 4 shows up in the second one? Pi over 4 is over there, right? I don't want that one. I need the second quadrant.
3 pi over 4?
Totally. Yes. Cool. 3 pi over 4, 5 pi over 4, 7 pi over 4. Do you guys see that? Maybe. So I love this stuff because it's new but not. It's reusing stuff we already know. As long as we already know it, it's not going to be as difficult, right? If you're still having trouble remembering what angle makes tangent -1, you're going to have some trouble with this. So how can I rewrite this? I can write it in the form R times cosine theta plus I sine theta. All right. I do not blame you at all if you don't yet see the efficacy of this. One of my favorite words. Here it is, beautiful. I have an example we're going to do in a minute that's going to be so kick-ass. It might be just me that thinks that. We'll find out. All right, how are we doing there so far? That's the concrete kind of stuff. And I keep trying to tell you, I don't blame you if you don't see the purpose of this. Is that better than this? These are the same. These are the same. Is that better than this? No, no, it isn't. Until you start to see what you can do with this form that you cannot do with that form. Then the whole thing opens up. All right. So I'm going to erase all this.
Can you do an example where you give us the equation like the z equals 2 and then we have to graph it from there?
Or
is that not something you would have to do?
Well, I mean, no. That totally could be. So, I mean, I thought you were going to say something else, but if I said, okay, graph this, I want you to realize how simple this will be. So if I gave you this here, right? And I said, graph that, you would get, you would get polar paper, right? Your polar graph, you go to pi over 6 and you go out 1, 2, 3, 4, right? And you would be done. Do you see what I'm saying?
Oh, okay, makes sense. Thank you.
Now, What I thought you were going to ask is, can you convert this back into normal form? The x plus, become an x plus yi. Why is that easy also? Because you know what cosine of pi over 6 is, right? What is cosine of pi over 6?
Rad 3 over 2.
Yes, so then rad 3 over 2 times 4 is 2 rad 3 plus I times, and sine of pi over 6, of course, would be
1/2.
Yeah, so let me write it like this, 1/2 I. So that would be what z looks like. And if you look at it, 2 rad 3 and a half. You know, kind of this, my scale sucks like all crazy. But if I go 2 rad 3 out and a half up, that looks to be about, you know, on my crappy ass scale anyway. Are you guys kind of with me? So going that way is beautiful. It's just do what this says to do. Going the other way is hard because it's trying to break this up into an angle and a radius. That's why this way's hard. This way's easy. Just put the shit back. Okay, I like it. I like it a lot. All right, so what we did last time is we said, okay, what if I have two of these things? Z1 is R1 cosine theta 1 plus I sine theta 1, and Z2 is R2 cosine theta 2 plus I sine theta 2. Right, and we did all the work about this. What happens if I do Z1 times Z2? I'm not going to redo this work. And we got R1 times R2 cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Become a 2. Right? You guys, I don't know if you guys remember that. You can always go back to the video and rewatch it. We actually multiplied this and this. I mean, I multiplied this and put it there. Yay. And then we foiled this thing out and we saw identities and we used the identities and then we got there. That's still not very impressive, to be honest. If I have two of these to multiply, I would actually multiply them if they look like this. That's just foiling whoop-de-doo, Jeff. Here's the trick. I want to do this next one before I get to division. Here we go. Here we go. Here we go. Here's the cool thing. You ready? What if I had to do z? What if I had z? Let me say I have z. Z equals r cosine theta plus I sine theta, right? That's z. What if I had to do z to the nth power? Z to the nth power. Wouldn't I have r? So imagine me writing z n times. Wouldn't I have r times r times r times r times r times r times n freaking times? So that would just become r to the n. Just like this became r1 times r2. R2. You guys semi with me out there? So just imagine a whole bunch of these and they all have the same r's. So I have n of them. So of course I'm going to have n r's. And what do I keep doing every time there's another one? Don't I just add the angles? Isn't that what we discovered here? So then I would have cosine of how many of these would I have?
N.
N of them. I like it. Right? Because if I did it twice, I would have 2 thetas. Theta plus theta is 2 theta. If I did it again, I would have theta plus theta plus theta. I have 3 thetas. But I'm going to do it n times. Plus I sine n theta. Now, all right, now stay with me. This is going to kick so much ass if you let it. Please let it kick ass. Let me stop for a minute. This kind of reminds me, I don't know if you guys remember when we proved this, and then we used what we got here to figure out what this was. Right? But we can push this even further. We can now figure out what n times of doing this thing will become. And now watch this. Now this is going to kick so much ass. All right. I'm going to take this away. So let me see. What did I use? Sure, it doesn't really matter. But let's say I have z equals 2 minus 3i. Now what? No. Say you want to do z to the 8th power. Are you with me out there? do you feel like writing 2 minus 3i 8 times, foiling about the 8th year, you're going insane, and you start writing all work and no play makes Jack a dull boy and red rum, it's all bad. And imagine if this was the 80th power. How about that? How about damn apples? So what I'm about to do will be as long as it takes me to do it, even if this was the 8 billionth power. I really want you guys to understand. That's where the real usefulness of this shit comes in. So first thing I've got to do, though, the one part that's going to take a minute is I got to write this in this form. Right? Let's stay with me. So how do we get R?
Square root of a squared plus b squared. Or
Yeah,
2
so we
squared.
square root of 4 plus 9, right? It's 13. By the way, make sure it's always the coefficients. Don't have that guy sneak in. So that when you square it, you get it negative and you get freaked out. Don't do that. It's the coefficients. And how do you get theta?
-3/2.
What about it? Theta can't be -3/2. It's the what of -3/2?
Inverse tangent.
I like it. Now, can you guys, let me see if you guys can trust me on this. I mean, if you do this in the calculator, what do you get?
Isn't it -3/2?
Is it? Yes, you're right. Sorry. So if you do this in the calculator, what do you get? You get something gross, don't you?
Negative 56.3099.
For
Blah blah blah. Yeah.
All right. Stay with me now. So I'm not going to write that shit. I'm going to have this be the angle. All right. Just. In fact, I'm going to use this symbol, and then I'm going to put this in at the end, so I don't have to look at it the whole time. Stay with me. This is cool. All right. Keep saying that, Jeff. So now I can write this as square root of 13 times cosine of what goes here for the problem I'm doing.
8.
8. Oh, I'm sorry. I'm going to write that next. Let me just write this. Cosine of theta plus I sine of theta, where this thing is theta. You guys with me? So z to the 8th is going to be the square root of 13 to the 8th times cosine of 8 times this. I'm just going to go ahead and write it in there right now. Yeah, you're fine, Jeff. Plus I sine of shit. This inverse tangent guy. Dadgummit. I should have just kept theta. I forgot the 8, didn't I? There's no room. I really want you guys, whatever power you're raising the complex number to becomes a multiplier in here because of the identities of trig functions. So this was the hardest part, but this is bullshit. This is nothing. And then I just do that instead of writing this thing 8 times. Are you kidding me? So now if you put this in the calculator, square root of 13 to the 8th power, believe it or not, is going to come out to a nice number. What's the square root of 13 to the 8th power?
20,561.
20,561 like that?
No, 28,500.
Oh, 28,000. Okay. Yeah, that sounds familiar. Yeah, and then I've got cosine of that plus I sine of that. Okay. Stay with me, everybody. I need room. That's my problem. So what's the cosine of that? Let me do this. Let's do this. Stay with me. I'm gonna distribute this through so we can put it all in the calculator at once. Give me a minute. Let me see. Where can I put this? I need more room. This is a long thing. I'm gonna put it up here. There we go. All right. So z to the 8th equals 28561. Is that right? Times cosine of inverse tangent of -3/2 plus 28561 I. Oh God, let's do this. Sine of, oh, did I figure my 8? I keep forgetting my poor little 8. Do we need the last thing? No, because I distributed. Let me stop for a minute. So all I did was take this big ass number and distribute it. So now I can put this whole damn thing in the calculator and you're going to be a little shocked maybe. Make sure that you're in, does it matter here? Yeah. That's a good question, Jeff. I guess it doesn't matter. No, it could be in radians or degrees. So let's see, 28561 times cosine of 8 times inverse tangent of -3/2. Let me just do that piece by itself. Where did you come from? Get out of there. Okay. Yeah. Is somebody able to do that in the calculator? Just that piece? Anybody? Just put it in just like this.
Just working on it. 1 second.
Sure.
I got -239.
Yes. Plus, and now I can just hit second enter and replace the cosine with the sine. That's the beautiful thing. Or you can put it all back in again if you want to be silly. So I really want you to understand what I just did. If you, I know, hold on. Where's my focus? Focus. Where are you? Well, shit and a half. Oh, there you are. All right. All right, here we go. Do you see that? So if I hit second enter, I think most of you guys know this. If I hit second enter, it brings that back up. And then I can just go back. Oh shit, this is gonna be interesting. All right, here we go, gentlemen. Screw it. I can go back, just hitting the over arrow, and change the cosine to a sine. So now I just hit sine, pop, because everything else is the same. It's just a sine there, right? I know that took a while, but that is a shortcut. All right, where am I? Whoa. Oh no. Okay, stop. Oh, there I am. All right, everything's good. I forgot what I got. -28560. So minus 28560 I. Now, just to bring this home, do you guys know you can do complex numbers in your calculator? Do you guys look above the period at the bottom of your calculator? What do you see? Do you guys, anybody? Above the period, you see an I. So you could actually, tell me if this doesn't work because you might not have it set up correctly. You can put 2 minus 3i to the 8th power in there using that I that's above the period. And if you do that, you get the same thing we just got. Now, some people take that the wrong way. Let me bring myself back. Oh, look at me. Some people take it the wrong way. They're like, well, shit, man, that was quick. I just do it in my calculator. Well, what's amazing is we didn't do the whole thing by hand, but we basically got it to a point by hand pretty far along. We needed some help with the square root of 13 to the 8th power, but you can't fault us for that. All right, maybe, I don't know. Maybe. Now, let's talk about division. How does division work with this notation? Time is, damn. So let's try this out. Oh shit. Well, that's all right. You guys got it. So again, let's set up the same Z1. Where's my good? Are you my good one? Yeah. Z1 equals R1 cosine theta 1 plus sine theta 1. And now I'm going to take Z2. And I'm going to divide these. So I might as well go ahead and set that up. Now, let me do this much. You ready? I'm going to do this much. Whew, I'm tired. What the shit can we do with this to simplify this? So just to give you a little push in the right direction, do you guys remember how to simplify this? Oh, whatever. How do I rationalize that denominator? Am I still blurry? There we go. Anybody? Do you guys remember how to?
Multiply top and bottom by rad 3 plus 3.
The conjugate. Just do the same damn thing here. Because I is rad -1. It's just a rad. So I can multiply top and bottom by the conjugate. I'm going to need some room. You need to get out of the way. By the way, so what we're doing right now is we're deriving a formula, right? Don't let friends drink and derive. Bad joke. I don't care. We're deriving a formula, so you're never going to have to do this yourself. I want you to know where this formula comes from. So we're going to multiply top and bottom by the conjugate of the bottom. So it's going to be cosine theta 2 minus I sine theta 2. So let's look at the bottom, because that's a little bit easier to handle. Bottom is sort of set up to work nice. So it's like the reason we use conjugate is so the middle terms cancel. So you get cosine theta 2 squared, right? Middle terms cancel. Minus I squared, which becomes plus, because I squared is -1, sine squared. Well, that kicks a lot of ass, right? That's beautiful, because the angles are the same. Therefore, this is equal to what?
1.
1. Kick ass. The top is a little bit different story. So let's see if you guys notice what this is. Where am I? Okay, cosine theta 1, cosine theta 2, minus I cosine theta 1, sine theta 2. Oh, shit. Oh, there's never enough room. Plus I sine theta 1, cosine theta 2, minus I squared, so plus sine theta 1, sine theta 2. Oh, Jeebus. So the bottom, look at all this room I could have used. All right, Jeff, whatever. And then here, does anyone see something about the non-I stuff? The stuff that ain't got no I's. Cosine, cosine, plus sine, sine. That sounds familiar, hopefully. Cosine, cosine, plus sine, sine.
Cosine
that?
A plus B.
Yes, so cosine of theta 1 plus theta 2, not plus. Remember, it's an asshole, so it's the opposite. Cosine theta 1 minus theta 2. Minus, so if I take a negative out of the I stuff, do I do that? I can't remember now. Do I have to do that? No, I don't want to do that. No, I don't have to do that. Plus, what is if I take an I out, what is this sine, cosine, sine, cosine. So that'll be sine, and it's minus, right? You guys with me? So it's sine, cosine minus sine, cosine, where the angles flip. So it's going to be sine of theta 1 minus theta 2. Why do I have so many parentheses? I don't know. And this is just 1 down here, so it's not even needed. Let me stop. This kind of makes sense. If I do z1 times, so this is z1 divided by z2. If I do z1 times z2, I add the angles and I multiply the r's. If I do z1 divided by z, I divide the r's and I subtract the angles. There's a beautiful analogy there. This one's not as useful, to be honest, but it's just there. It's just something to know. Okay. What'll really get neat in the future is when you start thinking about how do you take roots? How do I take a cube root or an eighth root of a complex number? We're not going to do that now. Don't freak out. That's not part of what we do. Okay. You guys okay with this? You guys, you always have to like when you get something analogous. Multiplying leads to adding, and dividing leads to dividing and subtracting. It's beautiful. It's so beautiful. Okay. Let me think. How much time we got? Not a lot. Dang gummit. I do want to talk a little bit about the next section. I have to. This next section is just so freaking cool. I can't remember what number it is, but the next section is about parameterization. I can't remember what they officially call it. Parametric. Yeah, parametric equations or whatever the hell they call it. So here, this is so, all right, I know I keep saying that. There's exceptionally cool shit happening here. So the idea behind, let me say this word, parameter. What do you guys think when I say the word parameter? Anybody think anything when I say parameter?
I think of perimeter.
I like it, sure. I don't blame you. They actually have nothing to do with each other, but that's all right. It's got that word association thing going on. Anybody else? Parameter? You got to work within operating parameters. You got to, have you never heard something like that? You have to be within parameters. No, okay. Parameters for a given situation aren't really variables, but like, for example, for a given kind of tire, there could be a parameter that discusses the tread wear over time. So if they have a different tire, it's a different parameter. And then you can set up an equation. Given that parameter, you can set up an equation for that tire, how much is going to be left after so much time. So a parameter is sort of a behind the scenes thing. It controls the other variables that show up later. This is exactly what we're going to do with this, is exactly that. So watch, this is kind of cool. If let me see, how can I introduce this in a different way? I really do like the idea. Have you guys ever seen an Etch-a-Sketch? Etch-a-Sketch, anybody? And you rotate the dials and the little thing goes around, right? And then you can hold it upside down, shake it, and it has anybody never seen an Etch-a-Sketch? Etch-a-Sketch, you know what I'm saying? I have a shirt that's huh?
I've seen those.
Okay, I have a shirt that's Etch-a-Sketch, Escher sketch. Anybody know MC Escher? Escher? MC Escher? No. It's a Escher sketch that has a hand coming out and it's drawing itself. But MC Escher. If you don't know MC Escher, look it up. Sorry, I'm trying to stay focused. So this could be like so one is the x-axis and the other one is the y-axis. If you go back to Etch-a-Sketch, That is the truth. So if I only rotate this dial, it'll go like this. Ooh, that's good, Jeff. And then if I rotate just this dial, it'll go like that. But if I rotate both of them, that's where it starts going diagonally. So it's kind of funny that we don't use Etch-a-Sketch more for math, because it just seems like such a mathematical thing. And it doesn't even ruin the fun of just, you know, playing with the damn thing. So let's say that I'm rotating this dial at some given time, right? So this is the formula that tells me after a second I've rotated this once. So the X rotations are equal to the time that goes by, but the Y rotations are twice as fast. Can you all picture that physically happening? So I'm rotating this guy and I'm rotating this guy twice as fast. What would it sketch out? What would it look like is the question. And we can do something called eliminate the parameter, right? Given these two, what is T? What do I know T is?
X.
X. So how can I rewrite this?
2x.
Yeah, now this is a remarkably basic, therefore not exciting example, right? This is kind of, oh, Jeff, good job. So what this is saying, why does this make sense? This really basic, silly example. If the y's are increasing twice as fast, then that is the freaking slope, isn't it? That's what slope means. So of course it's going to make the line y equals 2x. If I rotated them at the exact same rate, it would make the line y equals x. It would go directly diagonally at a 45-degree angle because they're both going at the same rate. Are you guys with me? Please. Okay. So if I make the y go twice as fast, it's going to go at an increased angle because I'm changing the y faster. So where does parametric equations become more interesting? And really what's going on here? So what if I had a setup like this instead? What if I had my x was like this? Yeah, dude. Yeah, sure. And my y followed this. So now here's the thing. I really want you to get this idea. There's several levels of this idea. The surface level is just eliminating the parameter and making a normal equation, normal equation. Whoop-de-doo. All right. The one that's a little bit underneath that is my x coordinates. If I were to list all the points that this would create, my x coordinates are following a sign. So what are my x coordinates going to go between? What are my x coordinates going to go between? What's the biggest my x value could be? Knowing that it's a sign there. What's the biggest sign can be? Maybe I should face you guys. What's the biggest sign can be? So you guys know I'm not talking to my board.
1.
My board. Yes, thank you. So the biggest x can be is 1. And the smallest x can be is -1. So x is going to go between these two evenly. Like, I really want you to understand. The x, so where's t? Where's t? There's no t-axis I've put up here. Over time, the x goes from -1 up to 1 and then back to -1 and then up to 1. At the same time, what is the y doing? Also going from -1 to 1, right? Now, it doesn't look like this. I want you to understand. It doesn't look like, why doesn't it look like what I just had where I was just tracing over the axis? Because they're doing this at the same time. I'm not sure why I switched these, but it doesn't matter. So at 0, what point am I at? If t is 0, what point am I at? If t is 0, what's x?
0,
Sorry?
0,
0. Kick ass, because sine is 0 is 0. If what's y then if t is 0?
1.
1. I love it. So I'm at this point. Right? Then what if I wait pi over 6 seconds? Now what point am I at?
1/2.
Yes, sine of pi over 6 is 1/2.
Rad 3/2.
I have no idea if you guys realize that what we're doing is we're tracing out the unit circle.
Mhm.
Right, and this kind of makes sense because if I eliminate the parameter, this is what this might be a little. This is a really neat way to do this. There's multiple ways to eliminate the parameter. You don't always solve for t and plug in. That kind of sucks. A better way to do it here is to square both sides. And then add the sides together. So I get x squared plus y squared equals
1.
1. And that is, of course, a
Circle.
the unit circle, kick ass, right? And that's all we're doing. We're creating a unit circle. But the one extra thing. So where is this 1/2 rad 3/2? Where is it? What quadrant?
1.
Yeah, first quadrant. So it's gonna be 1/2 rad 3/2. So it's gonna be like right there somewhere, maybe. Well, you can do better, Jeff. 1/2 rad 3/2, right there, right? So look what I'm gonna do. I'm gonna put little arrows. I know it's gonna do this, but I can put little arrows that shows me how it's moving. So that's the extra thing with parametric equations. As time goes from 0 up, or whatever they give me for this, they can give me some range for time. As it moves through its values, I can keep an arrow to show me how this thing is actually moving. So maybe this is a particle moving. And in fact, in this case, it would be that little freaky thing that's in the Etch-a-Sketch. And it's moving this way. Now, if it was moving that way, it would make the same picture, but you would have the arrows going the other way. So the arrows are a part of the graphs because they actually show what direction this is taking. So maybe some of you guys realize what's the usefulness of parametric equations for trajectory of rockets or missiles or baseballs or whatever, right? Because they come inherent with a trajectory. Which way are you going? Maybe. Oh, there's so many uses for parametric equations. It's insane. It's basically everywhere. All right, is that it? That's not a bad, what time is it? Yeah. That's not a bad introduction, I think. Okay, so what's really funny is we just did all this polar stuff, and then parametric equations, you're gonna go back to using an XY plane to graph parametric equations. Okay, and otherwise, that's enough for now, I think. So let me know if you need to hang out. Otherwise, you're free to go. Have a good weekend. Oh, man.
Thank you.
Bye.
Anytime.
Thank you.
See you. All right, guys.
Thank you
I'm
so
out
much.
of here. You're welcome.